In this segment, I want to talk about Chapter 9, Momentum. And so Chapter 9 is all about momentum, and we're going to focus specifically on conservation of linear momentum. So momentum is one of those words that we definitely use in everyday language, right? We might say that a semi-truck barreling down the highway has a lot of momentum, and that's a good use of the word. I think that most people bring into this class a pretty good intuitive sense of what momentum is. And that's good, because I'm not going to have to tweak your definition too much. So what is momentum? Well, this idea that, a semi-truck has a lot of momentum if it's moving quickly, and, maybe a small car moving slowly has less momentum, that's probably what your intuition tells you. And that's fine. So momentum is the product of mass and velocity. So that makes sense. A big object moving very fast has a lot of momentum. A small object moving slow has a small amount of momentum. You could have some intermediate case of a big object moving slow or a small object moving fast. Again, I think that you probably, that intuitive sense of momentum that you bring to the class probably contains most of that information. But it probably doesn't include the notion that it is a vector, right? And so that's one of the tricky aspects of momentum, I think. Momentum is mass times velocity. Since velocity is a vector, then that makes momentum a vector. We can think of momentum in a few different ways, and as we practice with it, you'll develop your own way of organizing it in your brain. Some people like to think of it as inertia in motion, and I think that's good. Remember, mass is inertia. Inertia and mass, for the purposes of this class, are synonyms. And so we can think about it as just mass in motion, you bet, as long as we remember that it's a vector mass in motion. Okay, as long as we remember the vector part of it, then that works. It's sort of an intuitive, sort of touchy-feely way of visualizing it. I like to think of it sometimes as velocity is a vector, right? And we're going to do scalar multiplication on the velocity. So really, momentum is just the velocity multiplied by the mass. The mass just scales it, right? So it's a scaled velocity, where the scaling happens according to the mass. That's maybe how I organize it more in my brain. But hey, there's a lot of different ways to visualize it. Now, the reason why we care about momentum, right? We can multiply any two things together, right? We can multiply mass squared times time divided by acceleration. I don't know. Is that interesting? No, it's not an interesting quantity. We certainly could do it, right? Well, why do we care about mass times velocity then? Why do we set this aside and put a box around it, call it momentum, and devote an entire chapter of the book to it? Well, because momentum in a wide variety of situations is conserved. Now, what does that mean? It means it stays the same. So, thus far in our journey through physics here, we've been talking about how things change in time, right? Position is where an object is at. How its position changes in time is its velocity. How its velocity changes in time is its acceleration. What causes accelerations? Forces, right? So it's all things changing. Dynamics. Even if we're talking about equilibrium, we're still talking about things moving, maybe. We're still talking about how things change. The first part of it has been all about how things change. We're going to enter into a couple of chapters here where we're going to talk about, okay, while all of that change is happening, are there any things that are always the same? And so the reason why momentum is so interesting is because of the law of conservation of momentum. The law of conservation of momentum says that the total momentum of any isolated system remains the same, right? And I'm introducing some new words, isolated system and all that stuff. Don't let that get you, right? The idea of conservation of momentum, it says that just in almost any interaction, the total momentum stays the same. The total momentum of what? The interacting objects, right? So if you've got a collection of objects and they're interacting, the total momentum remains the same. So what do I mean by isolated system? It means I'm not counting any of that stuff that's not interacting with my objects, right? What are my interacting objects? If you've got billiard balls colliding, your interacting objects are the billiard balls. Two cars collide. That's a typical setup for a conservation of momentum problem. In that case, your interacting objects are the two cars, right? And so that's what I mean by the isolated system. So that's just, I say isolated system and students start worrying about it because it's a technical sounding term. Don't let it get you. It's almost always fairly easy to identify the system. I could ask you questions where it was tricky. That's not going to be my intent. Okay. So the law of conservation of momentum says that if we include all the momentum for all of the interacting objects, then the total momentum of the system doesn't change as this interaction happens. And so we can write this in terms of math like this. It just says the final momentum is equal to the initial momentum. Notice it is a vector equation, so direction matters. And again, that's one of the things that gets tricky. But, in terms of components, we've got the final momentum and the initial momentum. And so what is the total momentum of the system? I don't know, maybe I've got 3 balls here. That one's going there, that one's going there, and that one's going there. P1, P2, P3. Okay, so what's the total momentum of the system? Well, it's just the vector addition of all of these, right? So we just need to include our vector signs, and then we can say that this is simply P1 plus P2 plus P3. Now, at this point, we've gotten pretty good at adding vectors, right? We just don't, this is not just regular numerical sort of addition, right? Scalar addition. This is vector addition, right? So the direction matters. But that's what we do, right? So however many total objects there are, the vector sum of those just doesn't change. It's a little bit surprising. And when I say almost any interaction, I'm talking about a wide variety of interactions, right? The classic example is 2 billiard balls run into each other. Great. Momentum before the collision is exactly the same as the total momentum after the collision. And that's fairly straightforward. But, even when things break, momentum is still conserved, right? So 2 cars crash into each other. Oh my gosh, there's braking, there's loud noises. We're losing all kinds of energy out of the system. What we don't lose is any momentum, right? Even though the cars got all crumpled up and somebody had to go to the hospital, it doesn't matter. The total momentum in that collision is still the same if I fire a bullet, right? Before I pull the trigger and after I pull the trigger, the total momentum of the system is the same, right? And you say, how can that be? Well, before I pull the trigger, the momentum of the gun and the bullet together is 0. It's not going anywhere. After I pull the trigger, the bullet has some momentum in that direction, and the gun has some momentum in that direction. Guess what? They are equal and opposite. The total momentum is still 0. It's a little bit surprising, even if we've got gunpowder involved in the situation. The total momentum before and after the interaction is still the same. All kinds of situations. And that's why it's such a powerful tool. Again, why do we care about mass times velocity? We care about it because it's conserved in so many different situations. And so, again, looking back at this, most of the time when we're dealing with vectors, right, then the way we strategize doing this is breaking them into x components and y components, right? So we're going to do the same thing here. If the total momentum, the total vector momentum, is conserved, then that means that the total initial momentum must equal the total final momentum in both the x direction and the y direction. So just like forces, where we can really treat them separately, right? Some of the forces in the x, some of the forces in the y. Put them together at the end, maybe. Same thing here. We can sum them, we can conserve momentum in the x, conserve momentum in the y if we need to, and if it was a two-dimensional problem, we could put it back together. We're going to focus on one-dimensional momentum in this class. So that's the basic idea. I do think it's important to recognize that what we're talking about here, it's not really a brand new idea. It's actually a consequence of Newton's third law. Remember that Newton's third law says that anytime 2 objects interact, the force on object A and the force on object B are exactly equal and opposite, right? So every force comes with an equal and opposite force pair, right? Those 2 forces are on 2 different objects. They're equal and opposite. They're always the same kind of forces, right? So imagine that we have an interaction. Well, and I've got a picture here, right? So imagine that ball 1 and ball 2 are moving towards each other, and they're going to have some interaction. Now, during that interaction, ball 2 exerts a force on 1, and ball 1 exerts a force on 2. Those forces are exactly equal and opposite. Furthermore, the time for both of them is the same, right? And so, right, in other words, like there's no way that ball 2 could push on ball 1 for longer than ball 1 pushed on ball 2, right? So the forces are equal. The time is equal for both of them. There's a lot that's equal here, right? And so what really ends up happening is that number 2 transfers some momentum to number 1. Number 1 transfers some momentum to number 2 via this Newton's third law interaction. And afterwards, we end up with the same thing. Any momentum that 2 lost went to 1. Any momentum that 1 lost went to 2. It all works out. And in this picture, if these were actually exactly equal masses, and they're nice hard balls that just bounce off without losing energy, then these velocities will exactly switch. So conservation of momentum is really just one logical step away from Newton's third law. It's not really a different idea, it's sort of a different face on the same idea. So we're going to have conservation problems, right? In this case, we're talking conservation of momentum. In the next chapter, we're going to introduce energy, and that's one of my favorite ideas to talk about is conservation of energy. That's one of the biggest, most important ideas in all of physics. And so the strategy we're going to develop here in momentum, we're going to apply that to energy in the next chapter. So I say this is for momentum problems, but we're going to be doing this before and after drawing here for a little while in this chapter and the next. So it should include all the stuff that we've been putting in our drawings. A definition of coordinates. We probably want to list our known and unknown values. A quick sketch of the situation if we need to. What's really going to be different, our new thing we're going to be introducing here, is we need a before and an after, right? So momentum is conserved, I say. When? Well, in some interaction. Well, usually it's fairly easy to identify what that interaction is. It's collision. It's pulling the trigger and the bullet, the gunpowder explodes. The bullet goes one way, the gun goes the other, right? That's the interaction. And so the before and after is we're going to draw a picture before the thing happens, and we're going to draw a picture after the thing happens. Okay, so that's what's really different. Okay, so here are some steps for solving conservation momentum problems. First of all, we're going to define our system. We're going to define the system so the net external forces on the system are 0. Okay, so this makes it sound trickier than it is. Defining your system, it's just the collection of interacting objects. And we just need to be sure that the net external forces on the system are 0. Or are very small compared to the forces of the interaction. You know, if I'm kicking a soccer ball, right, then, you know, if I'm kicking it really hard, I mean, we could be talking about kilonewtons of force easily that last for milliseconds, right? So a tiny, tiny amount of time, but actually truly very large forces. And in that case, you could easily neglect, you know, the tens of newtons of the weight of that soccer ball. So at any rate, we're going to pick our system so that it's just the interacting objects. And our system needs to have a net force of 0 on it. Again, it's not as tricky as that makes it sound. We're going to just draw a picture with the before and after scene, as we just discussed. And then we're going to apply conservation of momentum in the x and or y directions. And again, in this class, we're going to focus on one-dimensional momentum problems. And then we're going to solve. Okay, let's try an example. Okay, this one's about curling. Of course, curling's everybody's favorite sport. You got the big heavy stone. You try and slide it down the ice and get it to land on a target. I'm sure you probably all have curling practice after class. Here we go. A curling stone with a mass of 20 kilograms slides across the ice at 1.5 meters per second. It collides head-on with a stationary 0.16 kilogram hockey puck. After the collision, the puck's speed is 2.5 meters per second. What is the stone's final velocity? Okay, so this is a conservation of momentum problem. So let's start by drawing our picture. We've got a curling stone. And curling stones have a little handle on them, like all good stones should. It is 20 kilograms. And initially, it's moving with a velocity of 1.5 meters per second. And here's my hockey puck. And it is velocity equals 0. Okay? The mass of my puck, we might as well write that down, is 0.160 kilograms. So this is my before picture. Or initial. My after picture, well, what is the interaction? The interaction we're talking about is curling stone hits hockey puck, right? So what are our interacting objects? Well, it's the curling stone and the hockey puck, right? So this is our before picture. The after picture is my curling stone is still moving along, and we don't know what its velocity is. I'm assuming it's going to keep going in that direction. Honestly, my math will tell me. And now my hockey puck has some velocity, which is 2.5 meters per second. Okay, so that's my after picture. Great. In the interaction, the curling stone hits the hockey puck. Okay, what is my system? Well, my system is the curling stone and the hockey puck. Great. See, it's not that bad. It's not that bad. Is the net force on the system 0? Yeah. We've got some normal forces up. We've got some weights down, but they're not accelerating. And as long as there's no friction, then great. The net force on the system is 0. Or if the friction's just real small, this still works because the forces between the hockey puck and the curling stone are going to be happening for a very short amount of time, and they're going to have a very large magnitude. Okay, so that's our system. Not too bad. We should define a coordinate system, standard. Great. We've really only got any action in the x direction, right? We don't have anything going on in the y direction, so let's go ahead and conserve momentum in the x direction. We say momentum final equals momentum initial in the x, just to remind you of that. And we'll just go ahead and write out all the terms here, since this is the first problem we've done like this. So let's go ahead and write mass of the stone times velocity of the stone final plus mass of the puck, velocity of the puck final, equals mass of the stone, velocity of the stone, initially, plus mass of the puck, velocity of the puck, initially. Now, anything that's 0, we should go ahead and cancel out right now. That's just the initial velocity of the puck. So that is right here. So that's 0. We'll get rid of that. And now, what we can do is we're just solving for velocity of the stone final. And so we just want to subtract this over and divide by the mass of the stone. Okay, and now we just need to plug in some numbers. Okay, so here I have plugged in all of my numbers, and I ran my calculator, and I got, for the final velocity of my stone, and I guess I'll just write it up here, velocity stone final 1.48 meters per second. Okay, so does that make sense? Well, our stone was going 1.5, and you can see I need an extra sig fig to even make this count, which wasn't the problem. So initially its velocity was 1.50 meters per second, and now it's going 1.48 meters per second. It slowed down. Did we expect it to? Yeah. It only slowed down a tiny bit, though. Does that make sense? Oh, yeah. Look at this. This is like less than 1/100th of the mass, isn't it, right? So the puck has, the stone has a mass that's like more than 100 times greater than the mass of the puck. So I really don't expect the stone to slow down very much at all. And indeed it didn't, right? But what's important here is the total momentum was the same, right? The curling stone lost a little bit. The puck picked up some. How much did the puck pick up? Exactly the same amount that the curling stone lost. What was the mechanism? Well, Newton's third law, force pairs. If the curling stone pushes on the puck pushes on the curling stone. You can see the curling stone is pushing on the puck in that direction, giving it a net force in that direction, causing it to speed up. The puck pushes on the curling stone in this direction, giving it a net force in that direction, causing it to slow down. A little bit of momentum was transferred from the curling stone to the hockey puck. Not too bad. You know, conservation momentum is a nice way to look at rocket propulsion. A way to think about rocket propulsion is that, initially I've got this rocket, it's sitting here, it's got fuel on board, the total momentum is 0. The rocket shoots hot gases out, which causes it to accelerate in the upward direction, and it causes those gases to accelerate in the downward direction. Notice the rocket gains some momentum in the upward direction. The gases gain some momentum in the downward direction, but we can have positive momentum and negative momentum that still add together to make zero, right? So before the momentum was zero, after the momentum is still zero. It's a little bit tricky, isn't it? That's that vector nature of momentum that I was talking about. That's the part that maybe your intuition, maybe you didn't bring into this class, right? That we can have a total momentum of zero if you've got a lot of momentum in that direction and a lot of momentum in that direction. If they're equal, then the total momentum is still zero, right? That's a little bit of a tricky idea. You know, when rockets were first invented in the 20th century, there was a lot of discussion, actually, about would this work in space, right? Because, of course, people dreamed of going to the moon and things like that. So could you use a rocket to propel yourself in space? And good, smart people had debates about this. Would it work in space or would it not work in space? There was people who said, no, in space there's no air. And the way that this works is that the hot gases are pushing on the air, and the air pushes on the rocket. But it's just not really, that's not the best way to visualize this, because it turns out rockets do work in space, as we've seen. And so it's really easiest seen as a conservation of momentum problem. But, like I was just saying, Newton's third law and conservation of momentum, really, they're kind of two sides of the same coin. We can think of Newton's third law as giving rise to the idea of conservation of momentum. Okay. We can categorize different types of collisions. So these momentum problems, we're going to see them show up a lot as collisions. And, you know, that problem we just did, that's a collision, right? That was a collision between a curling stone and a hockey puck. That's a classic conservation momentum problem. Even something like shooting a gun, right? It's almost like a collision in reverse, right? We had the gun and the bullet together, and then they split apart and went their separate ways, right? So that's the kind of interactions that we typically apply conservation of momentum to. Now, we can categorize collisions according to their properties. And so this requires us to think a little bit ahead of ourselves, because we haven't really discussed energy yet. But we can call things an elastic collision, an inelastic collision, or a perfectly inelastic collision. And so for elastic collisions, both momentum and kinetic energy are conserved. What's kinetic energy? Well, it's energy of motion. Okay, that's usually not too tough for students. We're not going to talk about it officially until the next chapter, but we know what conserved means. Conserved means stays the same. So momentum is conserved and kinetic energy is conserved in an elastic collision. An approximation of that would be like a really nice bouncy ball that you drop it, it bounces off the floor, it comes back to basically the same height as you dropped it from. When it hits the ground, that would be an example of an elastic collision. Actually, like truly elastic collisions are hard to come up with, but you can put magnetic bumpers on things and have them have a collision where they never actually touch. That would be an elastic collision. In space, you can have this, right? And if an asteroid is coming towards the Earth from far, far, far out, and maybe it could come towards the Earth and go around the Earth and get slingshot back without ever actually touching the Earth. It's a gravity that pulls it in and then wraps it around and throws it out. Now that would also be an elastic collision. No kinetic energy is lost. There's no dissipative forces, no friction, no air resistance, no banging, no crushing, no breaking. All of those things would dissipate kinetic energy. We'll talk more about that in the next chapter. So really, for elastic collisions, honestly, we're going to kind of kick that down the road. We won't come back to those until after we've talked about energy. Inelastic collisions is where momentum is conserved, but kinetic energy is not. That's what we're going to focus on in this chapter, because we haven't talked about energy yet. And so inelastic collisions are, you know, most everything else, right? I mean, if I drop not a bouncy ball but a baseball, well, it doesn't reach down and grab it. It doesn't come up nearly as high. Energy is lost when it hit the ground. When this collides with the ground, that's an example of an inelastic collision. Now, anytime two things stick together, energy is lost. it's always the case that if a collision results in two objects sticking together, that energy is always lost. And so we can say a perfectly inelastic collision is when two objects stick together. An example would be, shooting a bullet into a block of wood. Here's your block of wood, the bullet comes in, it sticks, they move off together. That's an example of a perfectly inelastic collision, when two objects collide and move together. So this is just definitional memorization. But it does change the approach that you may need to take. Again, for right now, we're focusing on inelastic collisions, which can be separated into perfectly inelastic, stick together, inelastic, not perfectly inelastic though. That means that it was inelastic, but they did not stick together. Okay, let's do one more example. A 20-gram bullet is fired into a 0.5 kilogram block of wood where it lodges. If the bullet is traveling 400 meters per second before it hits the block, what is the speed of the bullet-block combo after the collision? Now, this is an example of a perfectly inelastic collision because the two objects collide and stick together. What's our system? It's the bullet in the block. See, it's not too bad. That's our interacting objects. Okay, so let's draw our before and after picture. We're going to use a standard coordinate system. Beforehand, we've got the bullet moving along here. The bullet equals initial, and that is 400 meters per second. And here's my block of wood. And we're going to call this V wood equals 0, right? There we go. And so our mass of our bullet, that's 20 grams. The mass of our wood, and I'm just using W because that way I don't have another B for block. So this is just mass of the wood block. And this is 0.5 kilograms, or 500 grams. Okay, so there's our before picture. We'll label it initial. My after picture, well, we have still my block of wood, but now my bullet is in my block of wood, and they are traveling off with some final velocity that we do not know. Okay? Defined our coordinate system, drew our pictures, identified our variables. Next, we should just apply conservation of momentum in the x direction and then solve. Remember, this means that P final equals P initial, and we're in the x direction. Well, again, we'll take an extra step and we'll write everything out, and then we'll plug in what we need to. Okay, so this is going to be the mass of the bullet, velocity of the bullet, final, plus mass of the wood, velocity of the wood, final equals mass of the bullet, velocity of the bullet, initially, plus mass of the wood, velocity of the wood, initially. Now, is there anything that's 0? Yes. The velocity of the wood initial was 0, so this term goes away. Can we do anything over here? We can. Isn't the velocity of the block final the same as the velocity of the wood final? They have a common final velocity. So what I could do is factor that out and write it like this. Great. We're looking for this final velocity. I'm one step of algebra away. We have V final equals mass of the bullet, velocity initial of the bullet, divided by mass of the bullet, plus mass of the wood. All right, well, let's just plug in our numbers. Mass of the bullet is 0.02 kilograms. That's 20 grams. Velocity of the bullet initially was 400 meters per second. And then this is the sum of the masses. So that is 0.5 kilograms plus 0.02 kilograms. And so now we run our calculator. Okay, so I ran my calculator here. I got 15 meters per second. Does that make sense? Sure. Notice I did get a positive value, right? We expect everything to keep moving in this direction. It's a vector, so a negative sign would indicate that it was going that way, and I don't expect that. But that is an error I see sometimes. If we had something going in this direction, you got to be sure you include your direction on that velocity. 15 meters per second, way slower than this, right? Yeah, that makes sense. The bullet has a much smaller mass, so yeah, together it's going to slow down a lot. Yeah, that makes sense. Let's think about it in terms of conservation of momentum. The bullet lost some momentum. Where did it go? Into the block. The block gained some momentum. How much momentum did the block gain? Exactly the same amount that the block lost. Momentum is conserved. It was transferred from one object to another, and they both moved off with a common final velocity because it is a perfectly inelastic collision.